So today we're going beyond the big five mass extinctions. Mass extinctions are severe, rapid, and global losses of biodiversity. And historically, paleontologists have recognized five major mass extinctions over the past 500 million years. However, mass extinctions, as we study them more, appear to have been much more common than we previously thought. There are a series of lesser but still catastrophic events in Earth's history: the Pleistocene megafaunal extinctions, the Eocene-Oligocene event, the Mid-Cretaceous event, the Pliensbachian-Toarchian, the Carnian, the Capitanian events, and others. And moreover, a number of the big five events may actually represent multiple pulses of mass extinction. So there may have been dozens of mass extinctions in the past half billion years. And what's more, as we move deeper into Earth's history, we see catastrophes that may have put the big five events to shame. The implication is that mass extinctions play a much larger role in evolution than we used to think. So first of all, how and why do species go extinct? Um, Before paleontologists could even start to ask this question, they first had to accept the reality of extinction, that species actually did go extinct. And the idea that species might vanish off the face of the earth and never come back wasn't really widely accepted until around 200 years ago, in fact. In the worldview that the science developed in the Enlightenment period in Europe, God made everything. The beasts of the earth gave rise to beasts after their kind, and the birds gave rise to birds of their kind, and plants produced seeds that produced more of their kind, and so on and so forth. And extinction in this worldview, which was a creationist worldview, it was kind of a weird thing because it suggested either God didn't know what he was doing if his creations vanished, or he didn't really care that much about some of his creations, and either of them is kind of a bit terrifying if you think about it. And extinction is also hard to study directly. It might seem obvious in retrospect. Hey, there's these dinosaurs out there. But think about it for a moment. I mean, look around. Do you see extinction happening? It's a really slow process. It can take hundreds of years, thousands of years, even hundreds of thousands of years. So someone watching it would no more be able to watch it happen in many cases than you can watch a mountain erode away or watch the stars move in the night sky. The stars aren't fixed, they move, but over the time spans that we deal with, human lifespans, the lifespans of civilizations, they're basically fixed. And species are a bit the same. It's very hard to watch them change over the course of a human lifespan. Another issue is that species can have huge ranges over hundreds, thousands, millions of square miles. So even if you see a species disappear from one small area, well, how do you know that it's extinct everywhere? So even in the case we actually watch it happen, as in the case of the dodo bird, where we saw these things wiped out, well, how could you know for certain there weren't still dodo birds lurking up in the mountains somewhere, or maybe on distant islands? How would you ever really know if you got the last one? So extinction is actually very difficult to study directly. And so because of this, people didn't readily accept the idea that species went extinct. Consider, for example, a case of uh, Thomas Jefferson and Jefferson's ground sloth. And yeah, it's that Thomas Jefferson, the President of the United States and one of the founders of the United States, the founding fathers. He also was kind of interested in science, and he studied the bone. These bones were discovered in a cave, a creature we now call Megalonyx, a giant ground sloth, and he wrote these up in 1799. And he thought that this creature, Megalonyx, might still exist somewhere, that they'd found a creature that had been wiped out on the East Coast, but still somewhere in the Western United States it survived on. And so he actually instructed Lewis and Clark, the explorers, as they explored the American West, to keep an eye out for a Megalonyx. Now, they didn't find one, obviously. This might sound silly or naive, but Jefferson is working before the time that the concept of extinction was widely accepted. And for that matter, there are species today, and we're not entirely sure if they're extinct or not. There's the ivory-billed woodpecker. No one's seen one in many, many years, but there's still people who hold out hope that one might still exist. No one's documented for certain Yangtze River dolphin. It's probably extinct, but we can't rule out the possibility that there's one or two still left out there somewhere, as unlikely as it is. So basically, when we're looking at the range of species that might take a long time to go extinct over hundreds and thousands of years, over large areas, it's a process that we struggle to observe directly. You cannot easily observe extinction directly. It's not part of our everyday experience. And so it just is something that, like, a lot of biologists didn't really think about seriously. So it was not modern animals, but the fossil record, the paleontological record, that was critical in showing that animals could go extinct by showing that there are animals in the past that are different from anything alive today. Baron Cuvier, who's often considered the father of paleontology, he is generally credited with establishing the reality of extinction. He described a mastodon skeleton from Ohio as a distinct species in 1806. And the mastodon was distinct from living African and Asian elephants. It was clearly an elephant, but from the teeth, the shape and the number and the arrangements of the cusps on the teeth was different from any elephant that we'd seen. And so, yeah, paleontologists, we tend to get into all these subtle anatomical details. Well, these details help us sketch out the big picture. In this case, these subtle details of tooth anatomy helped establish the reality of extinction, that the mastodon was not a living species, it was an extinct species, and Cuvier argued persuasively that it was very, very unlikely that an animal as large as the mastodon could exist somewhere and we just hadn't found it yet in some distant forest. We've basically been everywhere. If these animals existed around, we would have seen them. Therefore, it was extinct and no longer existed. And in many ways, this could be considered as marking the birth of paleontology. I mean, if you consider paleontology is the study of extinct life, we first have to understand and accept that life can become extinct before we can study extinct life. We have to establish that it does exist, and Cuvier does this. Cuvier would also describe creatures like the giant Mosasaurus. This is an enormous sea lizard, lived alongside and disappeared along with the dinosaurs, the end of the Cretaceous. This was a contemporary of the last dinosaurs, things like Triceratops and T-Rex. And Cuvier notes that there's this entire marine fauna of the Cretaceous, things like mosasaurs, but also ammonites, plesiosaurs, that are completely distinct from anything alive today, that these disappear from one stratigraphic horizon to another, and they never come back. It's not just one or two things vanishing, they're all vanishing together. Entire types of organisms are vanishing from the face of the earth simultaneously. And he argues that these extinctions are caused by events like flooding or the retreat of seas, and we're seeing the wholesale destruction of faunas with new ones replacing them. This extinction is rapid. It's hitting many species at once and over large areas. So Cuvier is not only recognizing the concept of extinction, he's helping define the concept of mass extinction. Now, some of the extinctions that Cuvier saw with a more complete fossil record, these now appear to be, we can kind of explain them in terms of gradual faunal turnover over millions of years, but his intuition was correct that there are in the fossil record rapid changes, and he's correctly identifying the disappearance of the Cretaceous fauna, things like mosasaurs and ammonites, as the result of a catastrophe rather than gradual processes. So Cuvier, in using catastrophes to explain evolution and extinction, or rather to explain extinction, he's a catastrophist. But how do we explain the fact that Earth is so diverse today if it's been subjected to catastrophic extinction events? How do we reconcile this with evolution? Well, Cuvier didn't try to reconcile it with evolution because he didn't really have a concept of evolution. He didn't believe in evolution, and he basically couldn't. Darwin's theory of evolution hadn't yet been developed. Darwin would write The Origin of Species in 1859, about 50 years after Cuvier's working. And so by default, pretty much everyone, including all the scientists, including the early paleontologists, were creationists. And not just paleontologists, biologists. I mean, Isaac Newton used the dates in the Bible to try to calculate that God made the earth and all living things 6,000 years ago. I mean, Isaac Newton, the father of physics. So they were creationists pretty much by default because they had, until Darwin came along, no alternative mechanism to explain the origin of biodiversity, either modern or fossil. And so we have these stories in the Bible. And God created great whales, and every living creature that moveth, which the waters brought forth abundantly, after their kind, and every winged fowl after his kind. And God saw that it was good. And God blessed them, saying, Be fruitful and multiply, and fill the waters of the sea. And God made the beasts of the earth after his kind, and cattle after their kind, and every living thing that creepeth upon the earth after his kind. And God saw that it was good. So that was the concept that people had of how biodiversity was created. And Darwin would meanwhile develop a very different view of extinction and evolution. Darwin came to understand that species evolved gradually, one species from another. They weren't created, they evolved. With successive slight modifications, one species could turn into different species or multiple species and create entirely new types of species. And he was spurred by looking at the Galapagos, and he saw the Galapagos had species that were not found anywhere else in the world, even though the habitats were similar. And he decided it was unlikely that God had created different species in similar habitats around the world. The idea of multiple creations basically made no sense to Darwin. And so Darwin tried to explain how this evolution of species into other species might happen within a naturalistic framework, trying to explain evolution and extinction via natural, everyday processes rather than extraordinary supernatural ones like acts of God. So he's trying to move away from catastrophes towards everyday processes. And in this, he's heavily influenced by geologists, guys like Hutton and Lyell. And these early geologists saw the rocks of the earth as formed by the slow action of everyday processes. Eruption could form rocks and erosion would grind them down again. Deposition could create sediments and sedimentary rocks. You could have the uplift of rock out of the sea or subsidence into the sea. And over eons, you would grind down rocks and form new rocks. The land would slowly rise up and subside into the sea. And just these gradual, imperceptible changes day after day could reshape the entire face of the earth. And Darwin reasoned in the same way, biological processes could gradually, incrementally reshape species. Processes like competition, predation, and mate choice could cause these gradual changes in species over time. One species could change into other species, or many species. And he was correct. And he also assumed that these gradual everyday processes were primarily responsible for extinction and the extinctions we were seeing in the fossil record. And Darwin was an incredibly deep, careful thinker. He's an amazing scientist. Origin of Species is well worth reading. There's a lot of ideas in there, and just seeing how Darwin approaches problems when he had so much less information to work with than we do is really extraordinary, and I think you can learn a lot from him. But I would argue he made one really big mistake. Which is not to diminish him as a scientist, but his big mistake was discounting mass extinction. And it's not that he didn't see it. He saw the evidence for it just as Cuvier had, and the evidence was better in Darwin's time because people had done more work, but he explained it away because it didn't fit his theories. He knew that there were distinct species in the Mesozoic, things like ammonites and belemnites and marine reptiles, and these were present in the Cretaceous rocks, and after the Cretaceous, they vanished. But it didn't fit his theory and his ideas about gradual change. So in 1859, writing in The Origin of Species, he argued that in fact extinction was gradual, and this big shift you see at the end of the Cretaceous was gradual. But there was something going on with the fossil record. There's a break in deposition. We might be missing 10 or 20 million years of gradual extinction, so it looks like it's very rapid. So it's kind of like fast forwarding from in a movie from like, say, midway through the movie right up to the final scene. You're missing a lot in the middle. This big jump going on there. And Darwin was tremendously influential, and this view would prevail for almost a century in paleontology. People agreed with Darwin that extinction was mostly gradual, driven by incremental changes over time, changes in climate, competition between species, and not primarily, and maybe not hardly any role for catastrophe in extinction. Finally, in the late 20th century, the idea of mass extinction made a big comeback. Now, there's no single piece of evidence that will overturn the idea of gradualism and reestablish catastrophism. Rather, it's a series of things. One of these is that we just developed a vastly better understanding of the fossil record than we had in Cuvier's time or Darwin's time. Paleontologists would describe thousands of species of trilobites, ammonites, dinosaurs, fossil clams, crinoids, microfossils, fossil pollen, fossil leaves. So we just had a much better idea of past diversity, and also the distribution of these species and families in space and time, exemplified by works like the Treatise on Invertebrate Paleontology, which was sort of the Bible of invertebrate invertebrate fossils, and just tried to describe all the various things that were out there and when they existed. And this improved fossil record helped show that the severe rapid turnover seen by Cuvier and Darwin was real, as we got more data, the pattern became more stark rather than disappearing. It wasn't an artifact of poor sampling. Better sampling actually showed these patterns, these rapid turnover events, were real. Another thing that happened was the development of stratigraphic frameworks to be able to look at all these things in time much more precisely. So scientists will use geology to try and figure out how old things are, but critically they use fossils. The fossils present in a bed can be used to help date that bed and correlate to other beds over huge distances around the world. They can track the succession of fossils through time, and so a fossil can establish where you are in relative time relative to older or younger fossils, and then correlate that laterally. So we know when things are happening, and critically we can correlate the fossil record in one part of the world to another part of the world. And by doing this, we can see that extinctions are global events happening simultaneously around the world. They're not regional events. And this is a major step forward, is having this stratigraphy and biostratigraphy, the stratigraphic framework of figuring out, okay, this succeeds this succeeds this, and then this thing succeeds that. And then another thing, so this might a bit surprisingly, an important development is the invention of nuclear physics, the discovery of radioactivity. Why is this so important? Because that allows us to use radioactive decay as a sort of clock. We can look at radioactive elements in rocks and look at how far they've broken down into their decay components, like uranium breaks down to lead. By looking at your lead-uranium ratio, you can get an idea of how much time has passed since that rock was formed. And this, for the first time, gave us the idea of absolute, not relative ages, like, the Mesozoic is before the Cenozoic. It gave you absolute ages, like this rock is 66 million years old. And we didn't have that before. We didn't know how old the Earth was. And there are big arguments about that between Darwin and physicists and things like that. So what this gave us, more fossils, the stratigraphic framework, the dates, it told us that the pattern Cuvier saw, and that Darwin saw too and explained away, is real. There are severe, rapid, and global changes in biodiversity, and these are the mass extinction events. So a couple of discoveries and a couple of papers really catalyzed a change in our thinking on mass extinctions. One of these, it's only one mass extinction, but kind of the most emblematic one, kind of a model for studying mass extinction, is the end Cretaceous mass extinction and the discovery of the iridium spike in the clay layer at the Cretaceous-Paleogene boundary. Iridium is a metal, an element that's quite rare on Earth, but it's abundant in asteroids, implying that the Cretaceous-Paleogene boundary is marked by the fallout of a giant asteroid. And paleontologists who spent their grad school careers and their time as professors learning that dinosaurs went extinct gradually due to changes in climate or sea level or competition with mammals, and had spent a long time arguing these ideas, they resisted this idea of catastrophic extinction furiously. But evidence kept coming in that there was an asteroid impact. We had these little beads of rock called spherules. This is rock that had been melted by the impact and cooled into sort of a hail of rock. We had shocked quartz. This is quartz metamorphosed by the tremendous pressure of impact. And then the crater, the giant Chicxulub crater under the Yucatan Peninsula in Mexico. So all these things helped persuade people that there was, in fact, a mass extinction and that this had wiped out the dinosaurs. And this idea that was once heretical and mocked and controversial is now widely accepted. One of the other major developments is the development of the mining of paleontological data to look for large-scale patterns. This has sometimes been called treatise mining in reference to the Treatise on Invertebrate Paleontology. I like to call it OPD, or other people's data. It's based on the analysis of existing data rather than generating new data. I say that, kind of a bit mockingly, maybe a bit disparagingly, but it's also a great way to work. We should all go out and gather new data, but you can also do a hell of a lot just by looking at data other people have gathered for questions that they maybe weren't interested in. And one of these was mass extinction. And this movement is led by people like Jack Sepkoski, David Raup, and Dave Jablonski. Jack Sepkoski was a student of the paleontologist and evolution biologist Stephen Jay Gould, and Gould encouraged him to dive into the literature and look for patterns. And wow, he found patterns, amazing patterns. So this was the other thing that really helped convince people of the reality of mass extinction. A survey of fossil diversity by Raup and Sepkoski, this is really an important paper in the history of paleontology, found evidence for a series of 5 major drops in diversity over the past 500 million years. These are the big five mass extinction events. So these are the Cretaceous Paleogene extinction at 66 million years ago that wipes out the dinosaurs. The Triassic Jurassic extinction 201 million years ago that kind of helps give rise to the dinosaurs. The Permian-Triassic mass extinction 252 million years ago. The Late Devonian extinction 372 to 359 million years ago. And the End-Ordovician extinction around 440 million years ago. And all of these, except for the Late Devonian event, were found to be statistical outliers from other intervals. So they're far above background levels and statistically distinct from them. So there's something different happening here. We have these 5 big events, and 4 of them were statistically distinguishable from just the rest of the data. What's curious is if you look at this, we talk about, the end Triassic, the end Permian, and Cretaceous. Why is it always the end of these boundaries? And that's not a coincidence. A large number of these extinctions coincide with geological stages, with these geological boundaries, and they end and begin major eras in the history of life. And that's not a coincidence. The division of life into the Paleozoic, Mesozoic, and Cenozoic, that's done on the basis of the fossils. It's implied in the name: Paleozoic, old life; Mesozoic, middle life; Cenozoic, recent life. These are not geological intervals, they're biological intervals. And so the rocks are tied into biological intervals rather than fossils being tied into rock intervals, I would argue. And so ammonites, for example, tell us we're in the Mesozoic. We don't find ammonites in the Devonian, we don't find them in the Cenozoic. Big mammals tell you the Cenozoic, and so on. It's fundamentally biology, evolution, extinction being mapped onto these rocks. These are faunal zones through time. We think of them as stratigraphic units. They're not. They're biological units fundamentally. And so if you're coming up with a system that's based on turnover life through time, the most obvious things are going to be these mass extinction events. It's like, wow, there's a big break here. I see this break around the world everywhere, and allows us me to correlate rocks. Everywhere I see Cretaceous rocks, with these species, and then in the aftermath, we always see these species, and that pattern is consistent around the world. So you're gonna seize on these mass extinction events. So basically, our geological time scale is to a large degree, it's a time scale of life and a time scale of mass extinctions and catastrophes. So extinction is real, mass extinction is real. How many mass extinctions were there? Now, you'll sometimes hear someone say something like, there were 5 mass extinctions in history. That's not true. And moreover, it's not even what the paper concluded. What the paper found, they found there were 5 big events that stood out as periods of exceptionally high turnover. They did not conclude that there were no other mass extinction events. They didn't say there were 5 mass extinctions. They're not the 5 mass extinctions, the big 5. The implication being there could be other events, other maybe not quite as big. By analogy, let's look at, say, musicians. The 5 top-selling musicians would probably include Michael Jackson, Elvis, the Beatles, Madonna, and Elton John. But you wouldn't say there were 5 rock stars in the history of music. Of course not. These are the big 5. It doesn't mean that The Who, the Rolling Stones, Bob Dylan, Taylor Swift, and the Velvet Underground weren't successful. They just didn't sell as many records as Elvis. So what I want to do today is go beyond the big 5 and ask, are there other mass extinction events? And if so, how many? What's their role in the evolution of life? And what does this tell us about the evolution of life? And in answer to our first question, are there other extinctions? At this point, it's pretty obvious. After all, we're in a mass extinction event right now. So the most obvious example of a mass extinction outside of the big 5 is an event starting around 100,000 years ago and which is ongoing. And this has been called the Pleistocene megafauna extinction because it wipes out a lot of Pleistocene megafauna. But I'd argue it continues past the Pleistocene into the Holocene and starts hitting more small species. So that's probably not the best name for it. I guess you'd call it the Pleistocene-Holocene extinction, perhaps. After humans evolved 300,000 years ago in Africa, they will spread out throughout Africa and then leave Africa into Eurasia and around the world. And we start seeing a series of mass extinctions of mammals associated with this expansion. We have around 50% of megafaunal species disappearing in Africa, then severe extinctions, much more severe, with almost all the megafauna disappearing in places like Australia, Eurasia, North America, and South America. And around the world, maybe something like 400 to 500 species of large mammal, also large birds and lizards and turtles, snakes will go extinct. And this is a small fraction of total biodiversity. I think something like maybe 1/100th of 1% of all species on Earth. It's not that many in the grand scheme of things, but start targeting particular niches. It's targeting your big herbivores. It's targeting your carnivores. You have entire families like ground sloths and nodoungulates going extinct. So it's radically restructuring ecosystems. And this is the event, incidentally, that convinces Cuvier of extinction. The mastodon is a victim of this mass extinction event. In the Holocene, which is after the end of the Ice Age, the extinctions will move out into distant islands as hunter-gatherers and early farmers discover sea travel. So in the Mediterranean, for example, we have island megafaunas. They're dwarf animals. They're kind of, relatively speaking, it's the largest animals in those habitats, but maybe not all that large. Crete, for example, has a fauna of dwarf elephants and deer and goats and hippos. And these are wiped out as humans move in. Similar faunas existed and disappeared on Cyprus and Malta and Sardinia in the Mediterranean. In Cuba and the Caribbean, we see island faunas of ground sloths and rodents, monkeys and birds disappearing. So the megafaunal extinctions move out to these islands after we have the extinction on the continents. And then we have the development of very sophisticated sailing by the Austronesian peoples. These are outrigger canoes and sails. And this allows people like the Indonesians and Polynesians to expand out of Southeast Asia and Indonesia to islands. And then we start seeing even more extinctions. So, for example, in Madagascar around 600 AD, the Malagasy reach Madagascar from Indonesia, and then they wipe out the local fauna, things like elephant birds and these giant gorilla-like ground lemurs. The Polynesians reach New Zealand around 1300 AD. They'll wipe out moas, adzebills, flightless rails, and giant eagles. And then the Polynesians will expand at the islands of Melanesia, Micronesia, Polynesia, and Hawaii. And it's been estimated that this expansion wipes out over 1,000 species, flightless rails and ducks and seabirds and passerines. So these are small habitats, small environments, not a lot of area, but they have a huge number of endemic species that are easily wiped out because they live in small areas. And so this, in terms of species loss, might be the largest number of species lost is by these expansions into island habitats. Then finally, in historic times, European explorers and colonists will discover far-flung places like Reunion Island, which is where the dodo is from. The dodo is wiped out. We'll see the extinction of passenger pigeons in the Americas, the bluebuck in South Africa, the Tasmanian wolf in Tasmania, et cetera, et cetera. And that continues on into modern times where destruction of habitats in places like the Amazon is wiping out species, and how many we're losing remains unknown. We're still watching species go extinct today, so we're still in this extinction pulse. Some of these are fairly recent extinctions, like the Po'o'uli bird in Hawaii. The Yangtze River dolphin in China has recently been thought to go extinct. But I'd argue that as our population stabilizes, as the human population stopped growing, and with the rise of the environmental movement, we're kind of taking more care of environments and species, the worst is quite likely behind us. And that might only be because we've already wiped out the most vulnerable species. But I'd argue that we live in the tail end of a mass extinction event. One of the most significant aspects of this extinction is that the first victims are actually other human species. As humans start to spread, we encounter other species of humans. There used to be maybe 10 or 12 different species that we lived alongside. And we will wipe out archaic Homo sapiens, Homo naledi and Homo rhodesiensis in Africa. Then we wipe out Neanderthals in Europe and the Middle East, wipe out Denisovans in Asia, Homo erectus, Homo floresiensis, and Homo luzonensis in Southeast Asia. So something like 9 or 10 different species of human may have been wiped out by our expansion. And I'd argue that this probably radically altered the evolution of our planet more than, say, Polynesians wiping out flightless birds on distant islands, because we're wiping out intelligent species. And this radically changed the direction of evolution when we become the sole remaining intelligent species, intelligent tool users on the planet. Now, this extinction, the Pleistocene-Holocene extinction, I guess that's the best name I can come up with for it. It's sometimes been called the sixth mass extinction. But while I would agree with calling that mass extinction, I strongly disagree with the numbering system. And there's lots of other mass extinctions out there, and just in the Cenozoic. We have, for example, a major extinction event. It's called the Grand Cuvier. I have terrible French, but that's French for big break, which is maybe I don't know, it doesn't sound technical enough, but the big break is identified on the basis of mammal fossils near Paris at the end of the Eocene. That's why it's French. When the planet enters the ice ages. So we have this sudden cooling and glaciation in Antarctica, and things get a lot colder, and a lot of things go extinct. A lot of mammals disappear on land. Things like these giant paleophyid sea snakes in the oceans go extinct. And, about 20 million years before that, at the end of the Paleocene period, 56 million years ago, we have the Paleocene-Eocene thermal maximum. This is a greenhouse event. The climates go up by something like 8 degrees Celsius in the period of 100,000 years or less. Very rapid pulsive warming. It's not nearly as severe as some events, but we do see major extinctions of benthic species in the oceans when the bottom waters are heated up. So there's a pulse of extinction there too. But the Cenozoic is relatively calm. If we go back to the Mesozoic, we start seeing a lot of really interesting extinction events. So the Middle Cretaceous has some really amazing species of dinosaurs. We have giant predators like Carcharodontosaurus and Giganotosaurus that were as big or bigger than T-Rex potentially. We have the aquatic Spinosaurus, and then we have these things disappearing along with primitive titanosaurs, the Rebbachisaurid sauropods, the Deltadromeus lineage. All these things are disappearing around 94 million years ago. And we also have extinctions happening in the seas about the same time. The last ichthyosaurs go extinct, the giant pliosaurs vanish. Somewhat later, the small pliosaurs go extinct, the complete extinction of the pliosaurs, and there's other families like the Cardabiodont sharks go extinct in the middle of the Turonian period. Exactly what's going on here is unclear, but there are a series of eruptions. There are these hyperthermal events, that is, extreme warming events, extreme warming very quickly, and we have oceanic anoxia, with these huge plankton blooms, and when the plankton dies, it shoves that carbon into the ocean where it rots and consumes oxygen. And so we have these huge anoxic events and these kind of black shales forming. So we have a series of mass extinction events happening around this time period. This is associated with oceanic anoxia again. This is oceanic anoxic event 2 across the Cenomanian-Turonian boundary. Again, it's caused by these plankton blooms, which are fed by terrestrial erosion, fertilizing the seas, and the severe warming. What's driving all this? What's driving these extinctions, the anoxia and the plankton blooms, the erosion, all this stuff? It seems to be driven by a huge eruption. It's been tied back to the eruption of the Kerguelen Plateau. Kerguelen is this island in the middle of nowhere. It's off of Antarctica. You may not have heard of it. There's not much out there except this little island that basically nobody lives on. But this platform was formed by this giant eruption, apparently, about 90 million years ago, and this seems to have been associated with an extinction event. There are a series of other anoxic events that we see in the marine fossil record, where you have these dark shales representing anoxic conditions being formed, anoxic bottom waters and extinctions associated with them. For example, there's oceanic anoxic event 1D, and it's quite possible that there's some significant extinctions of these horizons, but they're not quite as well studied. But we probably need to look at these more closely. And the early Cretaceous, there might be a series of minor extinction pulses associated with these oceanic anoxic events. So another key piece of evidence that this is in fact a mass extinction is an often overlooked characteristic of mass extinctions, and that's recovery. There's a lot of species around today. How is that possible with these mass extinctions? Well, it's because there's recoveries. After you wipe out a huge number of species, there's all these vacant niches. There's habitats where nothing lives. There's food sources that aren't being exploited. So the surviving lineages, radiate and produce new species that move into these niches. And following the Cenomanian-Turonian turnover, we're losing our big Carcharodontosaurs. We're losing a lot of these primitive sauropods. We're losing a lot of other species. We see massive radiations of things like tyrannosaurs, duckbills, ceratopsids, the saltosauroid and aeoliosaurian titanosaurs. So there's a series of major radiations of dinosaurs in the final 25 million years of the Cretaceous period. And this is, I think, pretty good evidence that there is, in fact, a mass extinction this time period. We also see radiations elsewhere in other groups. In the oceans, the mosasaurs stage a major radiation. They're taking over from the pliosaurs, from the ichthyosaurs. So this massive diversification of mosasaurs in the final 25 million years. In the seas, in the skies, certain groups of pterosaurs radiating, like the pteranodontoids. And we also see the modern birds. The ancestors of modern birds appear to be radiating, and the ancestors of modern mammals, the modern placental mammals, appear about the same time that we're getting Tyrannosaurus and duckbills and ceratopsids radiating. I don't think that's a coincidence. I think we're seeing massive radiation of all these things in the wake of the Cenomanian-Turonian transition. So this is probably one of the biggest extinctions in the Mesozoic, one of the biggest to hit dinosaurs before the asteroid gets them finally, and one of the most important turnover events of the Mesozoic. But wait, there's more. There's more extinctions. We have evidence for a pretty major extinction event near the end of the Jurassic, around 145 million years ago. So think of your classic Late Jurassic Morrison Formation dinosaur fauna. Brontosaurus, Apatosaurus, Diplodocus, Camarasaurus, Stegosaurus, Allosaurus, Ceratosaurus, Torvosaurus. All these things disappear. And not just the species level, all these families vanish. And they failed to reappear in the early Cretaceous in North America. In Europe, we're also losing a lot of stuff. We're losing the allosaurids, the megalosaurs, the turriosaurs. In Africa, this classic Tendaguru fauna in Tanzania, things like Brachiosaurus, Stegosaurus, and Barosaurus, these things all vanish. They never reappear in Africa. And then we're seeing the aftermath. In the early Cretaceous, we're seeing major radiations of groups like the Carcharodontosaurs. They become the top predators. We're seeing the first Titanosaurs start to appear. We're seeing iguanodonts radiate. The first Dromaeosaurs show up in the early Cretaceous. So again, look in the vertebrates. It sure looks like a mass extinction. The marine record is a little ambiguous. No one's identified like a clear extinction horizon. So I'm not really sure what's going on here. Is this just an extended period of high turnover? Is there a mass extinction event, perhaps a series of pulses of mass extinction? Maybe for some reason there's a severe extinction on land, but less so on the ocean. We don't really know. We just need to get a better fossil record here. But there's a lot of things at the end of the Jurassic that are hinting strongly at the idea of a mass extinction. Now, moving back in time, there's a major event in the Jurassic itself. And this is across the Pliensbachian and the Toarchian. And it's linked to the Karoo and Farrar eruptions, magmatic events in South Africa. And it also shows up in the form of an oceanogenic event, similar to what we see at the Cenomanian-Turonian boundary. It's been argued that this, however, is not a single big pulse of extinction, but up to 6 discrete pulses of extinction, smaller pulses, over a period of about 6 million years, from something like 186 million to 178 million, peaking at 183 million. And in the aftermath, we seem to have a major diversification of big sauropods, theropod dinosaurs, birds appear, and that seems to suggest that this event had a major effect on dinosaur evolution and may have spurred the diversification and radiation of surviving dinosaurs in the Jurassic. Going back to the Triassic, before the end Triassic mass extinction itself, we have a major extinction event in the Triassic, in the Carnian, about 232 to 234 million years ago. And at this time, we lose about 1/3 of marine genera, with major extinctions in ammonites and conodonts. On land, the mammal-like reptiles are hit hard. There's major floral changes. And dinosaurs stage a major radiation in the aftermath. In some ways, this is kind of sowing the seeds for the age of dinosaurs in the Jurassic. And it's associated with climate change events. It gets very warm, it gets very rainy, and it has also been associated with volcanic eruption. Up to 4 distinct pulses of eruption have been connected to this event, what they call the Carnian pluvial event. And the eruptions have been tracked back to the Wrangelian terrain. And it injects huge amounts of CO2 into the atmosphere, causing warming and increased rainfall. And curiously, turning to at least one paper I looked at, the Wrangelian terrain is currently in Alaska and Canada, but the rocks are actually linked to the Galapagos hotspot. So the Galapagos Islands, apparently, millions of years ago, about 250 million years ago, there's a major eruption event there, and this contributed to a mass extinction event that led to the diversification of dinosaurs. What a weird coincidence. So, in the Mesozoic, we've seen there are these multiple extinctions. It's not just the end Cretaceous, the end Triassic. We have extinctions, you know, in the middle of the Cretaceous, possibly the end of the Jurassic, in the Jurassic, in the Triassic. There's another interesting pattern we're seeing, however, as we get a better understanding of mass extinction. And that's that not only are all these little events, but some of the big five events may in fact be multiple pulses of extinction. There seem to be, for example, two distinct pulses of volcanic eruption and extinction at the Permian-Triassic boundary 252 million years ago. So we have this initial eruption and extinction, and then we have a second eruption about 200,000 years later that takes out even more species. So this is kind of 1-2 punch, not just a single big eruption event. So initial eruption, extinction, second eruption, even more species go out. Here's another graph of the same data, but it looks at it in a slightly different way, and it shows something kind of distinct, however. Even we're losing a lot of the species in the second event, we're losing entire families, like major groups, in the first extinction pulse. So which one is really doing the damage, or is the two in synchrony? A little hard to tease out, but it kind of tells us there's some complexity and nuance in these events that we didn't really anticipate. And it's not telling us that, okay, that's a gradual event, it's not catastrophic. It's kind of doubling down on catastrophism and saying not only is the Permo-Triassic event a catastrophic extinction, it's two catastrophes back to back. And that's what makes it so devastating potentially. As we move back into the Permian, again, we see this pattern of, you know, other smaller extinction events interspersed between the big five. So we have these at least two other major extinction events in the Permian itself. One of these is the Capitanian or Guadalupian mass extinction at 259 million years ago. This sees significant marine and terrestrial extinctions. One of the big groups that goes extinct in the Capitanian event are the dinocephalians, these kind of thick-headed mammal-like reptiles. And we also have Olson's extinction at 272 million years ago, which sees the extinction of finback pelycosaurs. These are animals like Dimetrodon, and the rise of more sophisticated mammal-like reptiles. So we're actually, the transition between the Permian and Triassic is marked by multiple extinction events spanning about 20 million years and becoming more frequent and more intense up to the Permo-Triassic boundary, where you have the most intense wave of extinction. But there's a whole series of extinctions leading up to this and contributing to this turnover event, not just this one big five event in isolation. We can also identify this pattern of pulsed extinction elsewhere. The late Devonian, we have a couple of small pulses of extinction, and then two big ones. The really big event at 372 million years ago is called the Kellwasser event. And then we have another, not quite as big, but still pretty big event at the very end of the Devonian, 359 million years ago, the Hangenberg event. This is again followed by a major radiation. Tetrapods move from the water onto the land after the Devonian in the Carboniferous. And that's where you see the early radiation of fully terrestrial tetrapods. Similarly, the late Ordovician seems to have a couple pulses of extinction. These are pretty closely spaced. Initial pulse of extinction, 445 million years ago, coinciding with cooling and glaciation. A second pulse, maybe 500,000 or a million years later, coinciding with warming. So again, we have a pulse of extinction, another pulse of extinction. This is a big five event, or is it actually like a couple of smaller events stacked closely together? In the Paleozoic, we also have pulses of extinction in marine communities in the Silurian, not big five events, but pretty big, and multiple events in the Cambrian. And these events are not well understood. As we go further back in time, the fossil record gets poorer. We don't have as many fossils. We can't sample as many areas, just not as many fossils have survived from that deep in time. We often don't have as good a constraint on the dates. So, you know, some of these events, could they be artifacts of just poor sampling? Possibly. It could also be that if we got better samples of these time periods, we would be seeing additional pulses of turnover that we're currently missing. So right now I'm mostly talking about numbers of mass extinction events, but do any patterns emerge out of this? And some really interesting patterns do emerge. The really striking thing is that when we can identify a cause of a mass extinction, most of the time it's a volcanic eruption. And this includes things like the Permo-Triassic mass extinction, the end Triassic mass extinction, also smaller events like the Cenomanian event, Pliensbachian-Toarchian, the Carnian pluvial event, and the Capitanian event. This idea that volcanoes are driving mass extinctions is especially true if we factor in pulsed extinctions and we count some of these extinction events as separate, because we have two pulses of volcanic eruption with two pulses of extinction, for example, at the Permian-Triassic boundary. We do see some evidence of just climate change, not obviously connected to volcanoes, playing a role. The Eocene-Oligocene transition is associated with cooling. The Ordovician is associated with cooling, then warming. So climate change seems to play a role. Obviously, volcanoes are driving climate change with all that CO2, and so they're playing a role that way as well. And curiously, we only have the one extinction, the end Cretaceous mass extinction, driven by an asteroid. At no other point in the past 500 million years are we clearly able to identify an extinction horizon linked to an iridium anomaly, linked to an impact horizon. So it's kind of a weird one-off, but far and away the most dangerous thing in the history of life has been volcanic eruptions, followed by climate change events, especially cooling, and then one asteroid, for what that's worth. I guess don't worry too much about the asteroid insurance. Definitely get the volcano insurance. So the concept of the big five mass extinctions, or even just Phanerozoic mass extinctions, these kind of little dozen or little 20 mass extinctions interspersed between them, is very, very limited. And that's because we're focusing on the past 500 million years, the Phanerozoic period. And this is where life gets complicated and big. And for some, okay, it's kind of obvious to do this. This is when we have good fossils. Animals get big. They start making skeletons and shells and clam shells and sea urchin spines and all that stuff we can study. And before then, it didn't really leave much of a fossil record. There's a lot less to study. But it's only the past, it's a little more than 10% of the entire history of life on Earth. And is it really likely that that first 90% of life's history didn't have any mass extinction events? And we do have evidence from the geological record that suggests major catastrophes. And these may have been driving extinctions as severe or more severe than any of the big five events. So there may have been major extinction events before the Phanerozoic. And in fact, the Phanerozoic may have been kicked off by a major mass extinction. And one of these is the Cambrian explosion, or to be more precise, the Cambrian explosion is a response to this mass extinction event. Now remember, adaptive radiations, like birds radiating the Cenozoic and mammals radiating the Cenozoic after the dinosaurs disappear, are a red flag for mass extinction. Mass extinctions are followed by radiation recovery. The biggest adaptive radiation in the history of life that we know of in the fossil record is the Cambrian explosion. And we see the emergence and radiation of complex animals, modern clades like arthropods, vertebrates, mollusks, brachiopods, echinoderms, polychaete worms. And we're seeing the evolution of advanced body plans, things like eyes, sophisticated brains, elaborate guts, limbs, and fins. So what's driving this exactly? Just before the Cambrian explosion, we see a very, very different world, a very different fossil record. And it's dominated by these bizarre creatures, these strange animals. Well, we think they're animals, but we're not entirely sure. We can't prove it. They're so weird. These things called the ediacarans, these bizarre organisms. And they form these bizarre mats and fronds, these weird spiral-shaped things that grow on the seafloor. They cannot be assigned to any known group of organisms. They seem to be unrelated to anything alive today. And we don't even know how they live. They're so different, they seem to occupy ecological niches that don't even exist anymore today. Now, these strange organisms, the ediacaran fauna, they disappear across the Ediacaran-Cambrian boundary just before the Cambrian explosion and the adaptive radiation. This happens 541 million years ago, along with some primitive shelly animals, things like Claudina and Namoclathus. These are like little corals or tube worms or something, but probably not related to modern corals or tube worms. We are seeing the near total extinction of this ecosystem, and it's being replaced by a completely different one in the aftermath that bears no resemblance to the first, either in terms of the membership of the ecosystem, like what families are there, or even the kinds of niches they occupy. This is not like Triceratops and Titanosaurs going extinct and being replaced by rhinoceroses and elephants. This is like modern Earth animals replacing alien animals. And I think this is a much bigger deal than the Big Five mass extinction. The Big Five mass extinction, like, okay, the membership kind of changes. It's like you're recasting a play, but it's basically the same play. This is like not just different actors. This is like a completely different play. When you get into the Phanerozoic, the Cambrian explosion, these creatures are doing completely different things. They have no connection to this bizarre Cambrian ecosystem. So in my mind, this extinction is far more severe. It's a much bigger transition, a much bigger deal, and I would expect a much bigger extinction than the Permo-Triassic event. Much more impactful. Again, this seems to be a staged event with two pulses separated by 10 million years. The first event sees these simple mat-like forms like Dickinsonia and these weird little kind of spirally creatures going extinct around 550 million years ago. The fronds survive for about 10 million years. Alongside, we see the radiation of these simple shelly animals like Claudina and Namacalathus. And then we have this much bigger pulse at the end of the Ediacaran period and the start of the Cambrian. And then we have the full-on Cambrian explosion as a recovery event. So one of the biggest evolutionary events in Earth's history, the Cambrian explosion, is triggered by a mass extinction event or perhaps multiple mass extinction events back to back. Now, as we move further back in time, it gets harder and harder to study mass extinction. The fossil record gets very patchy, and nothing's making shells or skeletons that can preserve. Everything's really tiny. A lot of life is microbial. There's only these very small, simple multicellular organisms like algae and fungi. So there's not a lot we can study in terms of life, and which is kind of how you identify mass extinctions ideally. But we are seeing evidence of massive catastrophes that were likely driving mass extinctions, things like the snowball glaciations. So in the Precambrian, there are at least three major glaciation events. They're far more severe than anything we've seen afterwards. One of these, in the Sturtian, from 717 to 660 million years ago, this spans almost 60 million years. We have the Marinoan glaciation from 654 million to 632 million years ago, almost 20 million years, and a relatively brief Baikonurian glaciation event at 547 million years ago. These ice ages will see all of Earth's land area and most of the seas covered by ice. Glaciers and sea ice would have extended down to the equator. There may have been a small slushy zone at the equator, or it may simply have frozen solid. This would have wiped out almost all terrestrial life. It is conceivable that there were some early terrestrial communities which have left no descendants, and these things have been wiped out. Probably would have driven major extinctions in the oceans. It would have limited the amount of oxygen and light reaching the sea, starving the seas of food and making things quite hostile there. I would imagine there were three major mass extinctions here, but we really kind of need a fossil record to study that. Another major catastrophe is the Great Oxygenation Event 2.4 billion years ago. Now, at this point, we see the rise and diversification and expansion of photosynthetic cyanobacteria. Photosynthesis becomes common for the first time. And this starts pumping massive amounts of oxygen into the atmosphere, and oxygen levels briefly approach modern levels. Now, oxygen is useful. We use oxygen to burn fuels like fats and sugars, and that's how we're able to get a lot of energy very quickly. We use oxygen. Oxygen is, however, highly reactive, even toxic. Oxidation causes the breakdown of biological molecules. It can damage your cells. It can damage your DNA if you lack adaptations to protect yourself against oxygen and repair the damage. It's toxic. So if you're not adapted to it, it's really, really bad for you. And so the sudden, the pouring all this oxygen into the atmosphere, basically a waste product of photosynthesis that things have not evolved to adapt to. This may have killed many or most microbes on Earth and wiped out entire lineages of microbes. And then the survivors would have had to adapt to this new environment. There is also, now this is the big oxygenation pulse, but there's also evidence of earlier, kind of more transient pulses of oxygenation, not quite as intensive, not as long lasting, and these might also have driven extinctions we can imagine. As we move back in time, we also start finding that extraterrestrial impacts, that is asteroid impacts, are becoming much, much more common. So between about 2.5 billion years ago and 3.5 billion years ago, we can identify at least 8 distinct layers of spherules. Again, these are spherules formed by extraterrestrial impact when it melts rock, and the rock condenses into these little stony, glassy beads. These are evidence of very large impacts. Some of them are significantly larger than the impact that wiped out the dinosaurs. So we're talking asteroid, the Chicxulub asteroid is on the order of 10 kilometers in diameter. These asteroid impacts, the asteroids themselves, are on the order of 20 or 30 kilometers in diameter, perhaps up to 50 or 60 kilometers in diameter. So we're looking at things that are anywhere from 10 times the mass of the asteroid that wiped out the dinosaurs to something maybe 200 times as big as the asteroid that wiped out the dinosaurs. And so these likely would have driven, major extinctions. Now you might look at this and say, well, okay, but there's only like bacteria and archaea back there anyway, right? Like, so how can this be driving mass extinctions if they're just like microbes? Well, if you actually look at the Cretaceous-Paleogene boundary, you'll see microbial extinctions, like little calcareous nanofossils and foraminifera. That's how we spotted the extinction. That's how we're able to see where it happens very precisely in the rocks, is we follow little microfossils, little single-celled organisms. We follow them up to the iridium layer and they vanish. And in a depauperate fauna of a few species, which tend to be very small because there's not a lot of food available, appear in the aftermath. So being a microbe doesn't necessarily protect you from an asteroid impact. So these things might have been driving mass extinctions, even if most of the life was quite small and quite simple and unicellular rather than complex dinosaurs and so forth. You could still have major mass extinction events of this period. And again, what we're kind of lacking right here is a detailed fossil record to try and tie into these asteroid impacts and see, is there in fact extinction happening at this time? And if we wind things all the way back to about 4 billion years ago, we now arrive at the late heavy bombardment. Now this is, I guess it's a bit debated, but they've looked at rocks, when the rocks from the moon, when they did the moon missions, they tried to look at the ages of some of the rocks and date the timing of various lunar impacts. And most of the dates they got on the impacts come from a fairly narrow period. So most of the evidence of impact that they found when they tried to date these impact rocks on the moon, the dates cluster between 3.8 and 4.1 billion years ago. And the idea is that most of the craters on the moon are forming at this time, this relatively brief period of time, 200-300 million years. And presumably when the moon is getting pummeled like this, the Earth is getting pummeled too. There's this kind of rain of asteroids. And this is called the late heavy bombardment. It's a bit debated. Some people think, well, the reason the dates cluster is just sampling rocks from the same big impact over and over again. But this is an idea that there was this major period of bombardment. And this would have driven massive extinctions, this very heavy bombardment of large asteroids around 4 billion years ago. It's been proposed that the late heavy bombardment was so intense that it would have wiped out any form of life on Earth and boiled the seas. So life could only have evolved after this impact event, after the bombardment event ended. And this would put constraints, obviously, on when life could have emerged. It's now kind of been, that's not widely accepted. It's thought that the larger impacts probably weren't large enough to boil the seas dry. They may have pasteurized them, that is, they may have raised the temperature in the seas to the point where they've been sterile to life. But even if they did, even if it killed everything in the seas, life could have survived deep underground in cave systems. You have extensive cave systems beneath Chicxulub today, beneath the crater in Mexico. There would have been similar cave systems below various asteroid impact sites in the early Earth, and life might have survived down there. It kind of cooked the seas, then it crawls back out and repopulates. So the late heavy bombardment may not have been a sterilizing event. It might not have wiped out Earth, but it might have, rendered large portions of Earth, entire oceans, uninhabitable, and would have seen incredibly high levels of extinction, with most forms of life on Earth wiped out, and a handful of surviving species giving rise to everything around today. So, conclusions. First, the 5 mass extinction events. No, There's way more than 5 mass extinction events. There's the megafaunal extinctions, the Eocene-Oligocene event, the Mid-Cretaceous event, End Jurassic, probably Pliensbachian-Toarchian, Carnian, Guadalupian, etc., etc., etc. And many of the big 5 events are themselves the result of multiple pulses of extinction. So there's a lot more than 5 mass extinction events there, a lot more. So we have these big extinctions, a handful of very, very large events, and many smaller events. And this probably follows something like a power law distribution or something very close to a power law distribution. That is, most events are small and there are rare extreme outliers. And this is a pattern we see kind of all over in lots of different systems that might seem very unconnected. It's described by something called the Pareto principle or the 80-20 rule. The Italian economist Pareto, for example, studying land ownership and wealth in Italy, found that 80% of land was owned by 20% of the families. So you have a few big landowners and many small ones. And you'll find the 80-20 principle everywhere. If you look at net worth, you have a few people who have billions and a lot of people who don't have very much. If you look at income, same thing. You have a few top earners and then a lot of people who don't make very much every year. Same thing would be true if you look at, say, sales of music or novels or movies. You have a rock star dynamic. The Rolling Stones make millions, and all these little bands that are playing on the street for quarters. Now, research suggests that a lot of disasters follow power law distributions. So if you look at the severity of events like blackouts, earthquakes, storms, and insurance companies have to study these disasters, they follow a power law distribution. You have a few small storms, you have many small storms every year, or maybe one big storm every year. And you have a few very large events. You have a very large magnitude storm that occurs maybe every 10 years. And then you have a storm of such magnitude you might only expect every 100 years. They call the 100-year storm. And extinctions might follow a similar pattern, this power law distribution of many small events, a few larger events, and a very few very large events. So there's probably a few really big extinctions, maybe the 5 really big ones in the past 500 million years. These are once in 100 million year events. There's maybe 10 or 20 smaller events. These are once in 10 million year events, or once in 20 million year events. And then lots and lots, hundreds of once in a million year events. And we might be overlooking a lot of these. Think, for example, how long it took us to recognize the End Cretaceous mass extinction, one of the big 5. It was overlooked and people were reluctant to identify it as a mass extinction event for over a century. It took us a long time to recognize a big 5 event. Many smaller events are going to be much more subtle, easier to overlook, easier to explain away. And there might be lots and lots of little minor extinction events out there, these once in 10 million year and once in a million year events that are there, and we're just not recognizing them, and maybe it's because we're just not even looking for them. The big 5 almost certainly aren't the biggest 5 extinctions in Earth's history. I would suggest the Ediacaran mass extinction is probably the largest extinction event in the fossil record that we know of. But as you go deeper in time, we are seeing extraordinarily severe catastrophes. We're seeing these global glaciations, the snowball events. We're seeing the great oxygenation event, the late heavy bombardment, and other massive asteroid impacts. These are probably driving mass extinction events as severe or more severe than the big 5. So I suspect it's statistically unlikely that the 5 largest events are all in the final 10% of life's history. It seems much more likely that a lot of the big extinction events are evenly dispersed, and some of the biggest, if not the biggest, are probably, and just because it spans so much time, that first 90% of history, the Precambrian, that's probably where the biggest mass extinction events are happening, but it's also where we just don't have the fossils to detect them. So what's it all mean? There's this incredible line that I first encountered in Herman Melville's Moby Dick, and it's from the very end of the book, after Ishmael survives the destruction of the whale ship Pequod and returns to tell his story to the reader. And it goes, "I only am escaped alone to tell thee." And it's from the King James Bible, and it references the book of Job. So what's the book of Job about? The book of Job is a rather extraordinary and unusual story from the Bible. And in the book of Job, God makes a bet with the devil. And the devil says that God's righteous servant Job only serves God because Job has been rewarded by God. And if God curses Job, Job will reject God. And so they have a bet. The devil bets God that if he destroys Job, Job will renounce him. And so God visits ruin upon Job, and a series of disasters befall him. Job loses his cattle, he loses his property, his family are killed. And it happens that 4 times a messenger comes to report the disaster that has befallen Job with this message: I only am escaped alone to tell thee. This messenger of disaster. And the story is about trying to make sense of a chaotic world and to reconcile destruction and evil with the idea of a just and orderly God. Why do bad things happen to good people? And there's this long discussion with a series of with some philosophers, and Job argues with them. And an angel shows up, and Job argues the angel. And finally, God appears out of a whirlwind, and they have an argument. And Job is like, God, man, I've been a good guy. What the hell? Why are you subjecting me to all these tests and trials and disasters and catastrophes? And God just returns and he says, who are you to question me? Would you catch Leviathan with a fishhook? Where were you when I laid the earth's foundation? Tell me, who laid its cornerstone while the morning stars sang together and all the angels shouted for joy? And the message is that there might be order, but that it might be order beyond your understanding. And who are you to question God? And Job never does renounce God, and God wins his bet, therefore. It's kind of a little weird, though. If God knows everything, why would you bet God? But then he's the devil, and the devil does strange things. And it's sort of a terrifying book, but it's an attempt to understand a chaotic world. The Bible isn't just trying to explain creation, but also destruction. And catastrophes are part of the biblical and the ancient world view, which is sort of rejected during the Enlightenment after Darwin and Newton, and people are trying to understand the world as a more orderly world and seek order and predictability and patterns in it. But while perhaps the Bible stories of disaster, the catastrophe of Job, the flood, aren't literally true, there might be some metaphorical truth to them, in the sense that sometimes the world has incredible disasters. And this was especially true in ancient times, when the world was, you could lose everything in a war, a plague, an earthquake, a famine. You could lose your whole family, your life, whole cities and civilizations could be ruined. So returning to this phrase, I only am survived alone to tell thee, this idea of lone survivors or very few survivors. You can see this pattern in the evolution of life. The lone survivor, the few survivors. If you look at a molecular clock, for example, of birds or of mammals, what you'll see is that you have this massive modern diversity, and it can trace that, all that diversity can be traced back to 12, 6, half a dozen species maybe that crossed the Cretaceous-Paleogene boundary. Out of the thousands of birds that lived in the Cretaceous period, all living birds descend from as few as 3 species that survived the asteroid impact. In this evolutionary tree, you can see extinction in it, because you have these long barren stems, and you've stripped off all the side branches. You've stripped away T-Rex and Triceratops, then Titanosaurs, then Pterosaurs, and all these things related to birds are gone. You just have these 3 lonely branches stretching back into the Cretaceous. So to argue that in the evolution of life, in the evolutionary tree, you can actually see mass extinction. You can see this in birds, you can see it in mammals, you can see it in other groups. What happens if you look at the tree of life? And you see something really extraordinary. The tree of life has just 2 lineages that survive until today from the first billion years of life's history on Earth. If you believe this molecular clock, and molecular clocks, they're a bit of a dark art, different analyses get different results. But if this result is true, you have 2 lineages, bacteria and archaea, that have descended from and survived the first billion years of life on Earth. And there's eukaryotes, where a hodgepodge of those two survivor lineages. But think about how incredible that is. As life is emerging, the first cells appear, early bacteria, early archaeans, there must have been this diversity of things. There must have been other things that are close to archaeans and close to bacteria and other lineages entirely. Like all these diverse microbial lineages in that first billion years, as life is initially emerging and it's experimenting and moving into new niches, some niches that maybe no longer exist. And all of those lineages have been stripped away except for two. I look at this and this is terrifying. Now, it is possible that a lot of these early microbes just kind of sucked and they just got out-competed by modern bacteria and modern archaeans, and that's why there's very few lineages that survived in this early time period. But another read is that there are multiple mass extinction events or a major mass extinction event that was so severe that even microbes were affected, and only two lineages survived, and maybe life came very close to being wiped out entirely. You look at this evolutionary tree and you see very, very few things have survived from the early Earth, and you wonder, man, what's going on there? So what's it all mean? Well, we descend from the survivors of multiple mass extinction events. Think about that. Your ancestors survived the Big Five, 10 or 20 other events in the Phanerozoic, the Ediacaran mass extinction, and even more severe catastrophes deeper in time over the preceding 4 billion years. I only am survived alone to tell thee, but we survived. We survived all that, our ancestors did at least. And not only did our ancestors survive, they thrived in the aftermath. After the dinosaurs went extinct, we saw the evolution of whales and bats and horses and our primate ancestors. It's sort of an evolutionary case of, life gives you lemons, so you make lemonade. Life gives you mass extinction, evolve something in the aftermath and take advantage of the open niches. Even, or perhaps especially in the worst disasters, there's opportunity. And it's really curious that our history is like this. Theoretically, we could look back at our evolutionary history and maybe it's like what Darwin would have expected, something very calm, very orderly, gradual evolution, gradual extinction, and we don't see that. And the fact that we are here and we see all this chaos in our history implies that maybe we're not here despite all that destruction, but maybe you're here partly because of it. Maybe all this chaos and destruction had a creative role to play in our evolution.